Okay, so my name is Jean-Francois Bousquet. Today we're going to be learning how to use Pspice to simulate circuits, simulate the behavior of circuits, predict how a circuit will behave in real life using software tools. So the software tool that we're going to be using today is going to be called Pspice. It's a simulator that is provided at the moment by Cadence. Mm, the name of the program that you launch is called Capture CIS Lite, and usually you'll find it in the ORCAD set of directories. ORCAD, ORCAD. So let's actually launch it. So when we launch ORCAD Capture, the first thing that you do is you're going to create yourself a new project. And in this case, what I'm going to be simulating is I'm going to be simulating a passive circuit. We're going to simulate its behavior in the time domain. We're eventually going to also evaluate its behavior in the frequency domain, as well as we're going to evaluate the DC operating point of the nets in the circuit. So we're going to provide a name to this project. The project is going to be of type Pspice analog or mixed analog digital. Because I'm going to be simulating a first order circuit, I'm going to give it a reasonable name that I'm going to be able to remember. First order RC demo. And it's going to be located in this set of directories. So I'm going to create my project based off of a template that's called analog ground symbol. It's going to contain a ground for us, so it's actually quite useful. Let's give it some time to launch. We can actually close all these applications that are in the way. And quit all this stuff that could be using some resources, and we don't want them to be using resources. That's all. Okay, so we're making our computer as simple as possible. Okay, so now I've got a couple of files that were created, some libraries. Okay, so when I create my project, by default, it comes with a set of libraries that contain components. We also have a main schematic, and the main schematic is going to be situated in this page. So, okay, interesting. So when I open my schematic, I have a ground, you see? So I have this ground component. The ground is a reference 0 volt, right? That's where that provides your reference. And what the manufacturer or the software provider provides to us is a net name here and a virtual connection. So I'll explain what that is throughout the tutorial. What we're going to do is we're going to go and add some components to this project. We can place components using this procedure. Okay, so as I said before, you can actually select only one library, and within each library you have a set of components, or you can go and select them all, right? And when you select them all, for example, you can pick a resistor. The resistor is in the library analog. So once you've selected it, you double click on it and you click where you want to place it here. If you want to rotate it, you're going to rotate it by pressing Shift R, I believe. Nope, that doesn't work. R? Yeah, R. Simply R will rotate the device. So you can find it here. This is the R. Right. Okay, so I've got a resistor. I don't think I want to rotate it, in fact. I'm also going to place a capacitor. Okay, so the capacitor I can place like this. And again, this one I could rotate it. Oh, it's already rotated this way. So that's C2. I don't want to, so as you can see, each component that you place is going to have a name. So in this case, that resistor is called R1, this capacitor is called C1. And it's got a value of 1 nanofarad by default. We can change the default value. We can make it 1 microfarad, I'm sorry, with a 1 kilohertz resistor. You have to find the time constant of the circuit so that we can actually analyze the proper range of time. Okay. We're going to connect this to, okay, we have different options here. So here you can see this, what is this thing here? What is this thing here? It's called a probe. I believe this is a probe. You know what? I'm going to copy it here. Okay, so like I said before, this is kind of like a virtual connection. I don't really have to go all the way there. This is, they've given it a name of ground zero. I give it a name of ground zero here too. Everything gets connected together. Okay, so now I'm at ground there. Let's actually also add a source. So the sources are in the library. Sources. Okay, so you have different types of sources. If you go down here, you've got voltage sources, a sinusoidal wave. This one's a little bit more versatile, the SRC one. This one's a sinusoidal wave, as I said before. There's an exponential source. There's a pulse source. I think this one's also interesting, the VPWL. It provides you a little bit of flexibility. VAC is useful to simulate AC simulations, and DC sources are batteries. Okay, so let's actually put in a sine wave. We're going to define the sine wave and its frequency. So I'm going to place it on my, I click it here, double click it here, and then I click it inside my project, inside my schematic. I'm going to wire the whole thing together. So to wire the whole thing, I'm going to like this, and like this. Okay, so as you can remember, this is grounded, right? This is okay. So I need to know my time constants on this thing. What are my time constants? My time constant is 1 tau. Tau is going to be equal to 1 times 10 to the minus 3, 1 millisecond, right? So I think if I place a sinusoidal wave with an amplitude, how do we do this, eh? I'm going to try it like this. Display properties. Okay, so the amplitude, we're going to put a 1 volt. Let's put a 5 volt. Okay. Frequency is going to be 1 kilohertz. A V offset, we can put a value of 2.5. That's what that does. Then we're going to put some names on our nets. So this is going to be V in. This. And we're going to put a V out as well. I've actually completed my schematic. Once I've completed my schematic, the next thing that I'm going to do is I'm going to simulate the schematic, and I'm going to say what type of simulation I want. So, well, actually what we could do is we could make sure that our net list is accurate. So it's going to create a net list for us now. So what it's going to do is this graphical interface is going to be converted to an equivalent file that describes the circuit in terms of connections. between components. So I've created my netlist. There's no, the Pspice netlist generation is complete. We're happy about that. We could actually view it. This is always interesting. So what do I have? I have, this is a file that describes all the components inside the, the schematic. Now, the first line here is just a header. Then I have a second line on which what's written here is, I say, there's a resistor of name R1. It's been between nodes Vin and Vout, and it's got a 1 kilo ohm resistance. This, I don't know what this means. Okay, so we'll ignore it for now. Same thing for C1. This one's in between node 0 and Vout. It's got a 1 microfarad capacitance, and we have a voltage source between the node 0 and ground. The type of voltage source is a sine wave, and the parameters of the sine wave are the following. Okay, so anyways, this is what we're going to be simulating. So to simulate it, I have to say, well, we're going to say what type of simulation we want. We're going to call this RC transient, okay, because we're going to be running a transient simulation. Okay, so this little thing popped up, and what do I want to do? I want to say, let's say that I run this for 2 periods of my sine wave. So I'm going to be running this for 2 milliseconds. 2 milliseconds. Okay, and that's probably not sufficient, but we're going to start with this. And we're going to give it a maximum step size, 0.01 millisecond. Okay, this is a general setting, time domain. Okay, we're doing a time domain analysis, and we're going to go apply. Okay, so this is a new type of simulation, and we're gonna. This is actually an interesting tab. We're going to display the probe window when the profile is open, display the probe window after the simulation is completed, and we're going to show all markers on open schematics. Okay, so what we're going to do is we need to put some markers on the schematic. What do we want to actually evaluate? What do we actually want to look at? Well, let's actually look at Vn. Can we expect what we're going to be getting at Vn? We're also going to be looking at Vout, like this. Okay, and okay, so again, do we know what to expect at Vout? How would we know? Well, we'd have to get the impedance of the capacitor here, and we do voltage division for the frequency that is for the operating frequency. If we're trying to solve this in the time domain, it becomes a little bit complicated, but we're going to be doing a transient simulation, so might as well show it here. So this is a voltage level marker, this is a voltage differential marker. Now I can actually put a current marker. So why don't I put a current in that's entering this node of the resistance? Okay, I don't really need to put one here because it's going to be the same value, obviously. Okay, so let's simulate this now. Pspice, we're going to run it. Okay, and hopefully this works. I'm going to find that a window opens up. Okay, so this window opens up. I wish, okay, wait, we're going to save this. And I'm surprised that we don't see the markers here. I think we should be able to see the markers. Something opened, but actually they don't give me any traces, which is a little bit weird. There we go. Okay, now it worked. Okay, so I don't know why it didn't work the first time. Now, what do we see? We see input voltage. Okay, so what are we seeing here? We see input voltage. Do I see two periods of my input sine wave? Yes, I do. This is V out. Okay, excellent. What about this guy? This guy is my current R1 and entering R1, but it's so small I can't actually make it out here. So I can't really plot it on the same axis. I have different options to do this to represent I properly. I could add a y-axis, or I could add a plot to the window. The two options are available. I personally find it's easier to add a plot to the window, so now I have a second plot. What I'm going to do is I'm going to delete my IR1 from here, and I'm going to put it here. So you see now I can actually see that I have 10 milliamps. Before the scaling was not accurate, so that I couldn't know. Oh, another thing that you may notice is that there's a DC offset on this thing. So that's another interesting thing to look at. Okay, so now what I can do is I can actually put some markers on here. Okay, so I can plot with some markers. Where do I add markers? Yes, a cursor. So we're going to display our cursor. You have actually two cursors. One of the, if you click with the left button, it's going to place one of the two markers, and if you click with the I believe with the right button, it's going to give you another marker, okay? And if you look down here, what do I have? I have Y1, Y2, Y1, Y2, and there should also be a Y1 minus Y2, so it's a delta, right? So let's say I put my Y1 here at the maximum. What is this? Yeah, this is the currents. Okay, so we're actually going to put our cursors down here instead. Can I put the cursors? Right, okay, so I'm going to put my cursors. One of them is going to be here, the other one's going to be on V out. So if I place it here, and I place this one here, I can actually see the time difference. Y1, can I actually make out the time difference? There should be a way for me to get the time difference between the two, not just the Y's. Y1 minus Y2. This is cursor 1, cursor 2. Max, what do I see here? There's a way to also extrapolate the time, right? So, oh, these are the X values, right? And this is the difference between the two. So as you can see, the distance is 277 microseconds there. Okay. So this is sort of how you manipulate the results. You can actually add additional traces using the database that gets open here. Usually when I look at the database, I remove certain components that I don't think are interesting. But you can browse through here and you can find the components easily. You can also modify the outputs using functions. So you could try to plot the RMS value, the phase of a signal, min, the maximum of a signal, the log and base 10. So these are mathematical formulas that you can apply to the signals, and the trace expression goes down here. So for example, if I wanted to do well, we're going to do this in the frequency domain, okay, because right now this is not it's not applicable, but there you go. This is the output of your simulation result here, okay, for this circuit. One more thing that we can look at is we could look at the bias point. Can I see? Oh yeah, right. Okay, so my voltage operating point is shown here, and the current that is shown here, this is the DC current that's flowing through my circuit. Okay? So this is expected, right? There's no DC current flowing through that circuit because the capacitor is an open circuit. Okay. The next thing that we're going to do is we're actually going to run, instead of running a time domain simulation, we're going to run a frequency domain simulation. When you do this, you cannot use a vSyn type of source. You have to use a VAC type of source. VAC type of source. Okay, so by default, the amplitude of that input source is 1 volt. And since we're running a frequency domain analysis, we're actually gonna edit our simulation profile. And instead of saying that we're going to be doing a time domain analysis, we're going to be doing an AC sweep. We're going to be doing an AC sweep that in a logarithmic scale. Usually you want to do a logarithmic scale so that you have a good representation of a large frequency band. We're going to start at a frequency of 100 hertz. Even 100 hertz is probably not low enough. And we're going to go up to 1 megahertz. I'm going to represent 11 points per decade, or 101 points per decade. It's going to be a little bit more, the resolution is going to be a lot better. Okay, so we're going to try it like this. Now we can run the simulation. Okay, we're going to see if this works. I'm going to have a whole new set of data that's going to be plotted. Beautiful. Okay, so this over here is my Vin. My Vin is constant at a value of 1. This is my Vout. And this one changes as a function of frequency. This one over here is my I. So again, what I could do is I could add a trace. Okay, we're going to add a, no, not a trace, I'm sorry. We're going to add a plot to the window. We're going to remove the current from here. We're going to put it up here. Okay, so as the frequency increases the current here, it becomes like we sort of see the effect of a high pass filter for the current. Now I see Vin. Vin's not all that interesting. What we're looking at, we would like to be evaluating the transfer function of this circuit. So the transfer function of this circuit, what I'd like to be doing is I'd like to be evaluating the Vout over Vin. So we're going to delete this. We're going to delete this guy. Can I delete it? I thought I could delete this one. How do I delete it again? I thought I could delete it like this. No? Okay. Anyways, it's not that important. What we're going to do is we're going to look at this one, and we're going to say, I want to represent this, the transfer function, and I want to represent it on the dB scale. So 20 times log in base 10 of the voltage Vout divided by the voltage of Vin. Vn, and I think I wrote it properly. 20 log in base 10. Probably it may need to be large cap. So we're gonna try it formally like this. Beautiful. Okay, so what do I see? So I'm representing it on the dB scale. We're gonna delete this guy. I know I can delete him. Okay, so I think now I can. Oh, no, did I do that? Okay, so we're actually gonna add a plot to the window. We're gonna add a trace. We want to do Vout. And we're gonna do it 20 times log in base 10 a V out. Okay, because V in is always at 1, we don't really need to put them. It's okay, so this is good. What's the problem here? Is this a formal Bode plot? It's not, because this on this axis, it's on a linear scale. It's on a linear scale, right? Am I wrong? No, it's on a linear scale. So I'd like to replace this. I'd like to show these. On a log scale. Okay, so now I should be seeing this on a log scale. Where's my 10 megahertz? Auto range, user defined, scale, log. 10 hertz, 100 hertz, 1 kilohertz. But no, this is actually a logarithmic scale. It's just I've got a bit much. Where's my cutoff frequency? Where's my cutoff frequency? It's around here. Well, I can place a cursor. Okay, where's my cursor? We're actually going to move until we have 3 dBs of loss. Where's my cursor? Y1 here. Okay, you can see it. We're at 300 hertz. -8. This is -8 dB. We're going to make it go here. -3 dB. Our -3 dB is at a frequency of 159 hertz. So we should double check that it matches theory. So there we go. We just created ourselves a frequency domain simulation and a frequency domain analysis. Okay, and again, just want to highlight the fact that what our representation here, I originally thought this was a linear scale, but it's not. It's in a logarithmic scale. It's just you've got one decade here, another decade here, another decade here, another decade here, and another decade here. It's probably better. I could probably cut this down to 100 kilohertz. I could rerun this to show you a little bit more in detail on the right range of frequencies. So instead of saying 1 meg, I'm going to go 0.1 meg. Okay, I'm going to rerun this one more time. And I think it's going to delete everything, eh? But it's not the end of the world. We know how to fix this. I think we know how to fix this. We don't really need the current this time. We can delete this guy. We can delete this guy as well. And what we can do with this guy is we can simply edit him. Oops. Here, double click on here. And then I'm going to go 20 log of V out. 20 times log in base 10 V out. Okay, beautiful. Okay, and then we're going to place our cursor. Where's my 3 dB plot? My 3 dB cutoff frequency. 3 dB cutoff frequency. Right now I'm at -1.5. I'm going to go just a little lower. Gone too far. We're almost there. Oh, again, I'm bad. It's not good. We said what was it's around here, eh? Almost there. 159, 55. Actually, here we go. Sorry, it's 159 here. Okay, so the frequency is 159 and the attenuation is 3 dB. Okay, great. So that completes my introduction to Pspice, and I hope this will help you get started with the simulation tool. If you need any questions, you can fire them off to my email at jbousquet@dal.ca. Thanks very much for your attention. Let's close this up. So we're gonna be testing whether the volume works carefully. Okay, thanks. Bye bye.